Welcome back to The Explainer. Today, we're diving into an absolutely mind-bending reality. Because, thanks to some brand new tools and truly unprecedented observations, we are fundamentally rewriting our entire understanding of the universe. And you know what? It all centers around the ultimate cosmic heavyweights, black holes.
So I want you to ask yourself a question. What if our entire model of the universe is just wrong? I know, it sounds straight out of science fiction, but recent observations of black holes, looking at everything from their incredibly violent collisions to their ancient, quiet origins in the early universe, well, they're challenging literally everything we thought we knew. The new data is just breaking our models left and right, and quite frankly, astrophysicists are scrambling to keep up.
But here's the thing. This isn't actually a crisis. It's a massive opportunity. As astrophysicist Simon Burr puts it, this is the dream of every physicist. Find something wrong in our understanding so we can discover something new and profound. We are standing right on the threshold of an incredibly exciting era of discovery. The universe is speaking to us in completely new ways, and for the first time, we're finally learning how to listen to it.
Okay, part one, the cosmic symphony. For centuries, we've really only been able to look at the cosmos. But now we're actually hearing its background hum. To actually hear this hum, scientists use something called a pulsar timing array, or a PTA for short. You can kind of think of this as a giant, galaxy-sized detector. So the Nanograph collaboration takes these dead, rapidly spinning stars called millisecond pulsars, and they use them like incredibly precise cosmic metronomes. By measuring just the tiniest delays in the pulses of these stars, scientists can literally listen to the overlapping ripples of space-time. These ripples are caused by supermassive black hole binaries swirling around over the entire 13.8 billion-year age of the universe.
Now, the scale here is almost impossible to wrap your head around. We're talking about gravitational wavelengths from these supermassive binaries that are measured in light years. Light years. It's exactly like tossing giant boulders into a cosmic pond and then watching those massive overlapping ripples wash over our entire galaxy. It's this incredibly slow, rhythmic stretching and squeezing of space-time itself.
Moving on to part two, hearing black hole collisions. So now we're transitioning away from that slow, ancient background hum of the supermassive giants. Instead, we're looking at the violent, rapid collisions of smaller black holes that we can detect right here on Earth. On the one hand, you have your pulsar timing arrays picking up these low-frequency waves from binaries that take millions of years just to orbit each other once. But on the other hand, we have ground-based observatories, things like the LIGO-Virgo-Cagra network. And they detect high-frequency waves. We're talking about the final, incredibly violent fractions of a single second when stellar mass black holes finally collide and merge together.
And guys, this network is getting astonishingly good at this. Take this number for example, 76.9. That's the signal-to-noise ratio for an event called GW 251114. Basically, that just means it was incredibly loud and clear, cutting right through all the random cosmic static. That signal actually reached Earth on January 14, 2025, and because it was so pristine, it allowed scientists to perform the most accurate tests of Einstein's general relativity ever conducted. It even let them confirm Stephen Hawking's black hole area theorem, which dictates that a black hole's surface area can literally never decrease over time.
But here is where a pretty massive plot twist emerges from the newest detection catalogs. Scientists have actually discovered evidence of what they call second-generation black holes. These are absolute beasts with masses 10 to 20 times that of our Sun, and they are spinning extremely rapidly. Their unique properties strongly suggest that they didn't just form from a regular dying star. Nope. They were born from the ashes of previous black hole collisions in incredibly dense star clusters. So they're just out there, merging repeatedly and building themselves up over time. Crazy, right?
All right, let's jump to part three. Weighing ancient, invisible giants.
So how exactly do you go about weighing something you can't even see? Well, astronomers pulled off this incredible three-step cosmic trick using the James Webb Space Telescope. First, they found a massive foreground galaxy cluster. Second, they used its immense gravity as a giant natural magnifying glass. That's a technique known as gravitational lensing. And it let them view a much, much more distant galaxy. And finally, step 3. Using JWST's ridiculously sharp vision, they measured the boosted velocity of stars orbiting the hidden center of that distant galaxy. The stars were simply moving way faster than they should have been, which completely gave away the mass of the invisible object that was pulling on them.
And the result of that measurement? 6 billion. That is the absolutely staggering solar mass of the dormant black hole sitting at the center of the galaxy MRGM 0138. It is an invisible, quiet giant packing 6 billion times the mass of our Sun, and it was sitting right there just 3 billion years after the Big Bang. This was actually the very first direct mass measurement of a dormant black hole from the early universe. It proved once and for all that these monsters existed way, way before we ever thought it was possible.
Which brings us to part 4, rewriting the universe's history.
You see, these massive discoveries in the early universe are completely breaking our existing models of how and when galaxies actually formed. We're finding these total universe breaker objects. Take UHC-1, for example. It's a 10 million solar mass black hole, existing just 470 million years after the Big Bang. And then there's Abell 2744-QSO-1, which is up to 50 million solar masses just 700 million years in. So you really have to ask yourself, how on earth did black holes get so big and so incredibly fast when the universe itself was basically just a toddler?
There is a really stark, puzzling contrast here. Because in our local modern universe, a central supermassive black hole usually makes up a tiny, tiny fraction of its host galaxy's total mass. Usually it's roughly 1 to 1,000. But in the early universe, well, in the case of Abell 2744-QSO-1, the black hole to stellar mass ratio is near 1 to 1. The black hole makes up a massive fraction of the entire galaxy's mass. This really suggests that back in the cosmic dawn, black holes might have actually grown before or maybe right alongside the galaxies around them. That totally upends our standard models.
Okay, part 5, our gravastar's rear. Now prepare yourself because this introduces the biggest plot twist of all. What if some of the supermassive objects we've been detecting aren't actually black holes at all? A really groundbreaking 2023 analysis led by physicists at the University of Hawaii found something deeply strange. They discovered massive black holes growing in mass over time at exactly the same rate that dark energy is expected to grow as the universe expands. Now remember, dark energy is that colossally powerful, mysterious force that's accelerating the expansion of the entire cosmos. So could these massive objects actually be connected to it?
Well, this brings us to the utterly mind-bending concept of gravastars. So a traditional black hole features a singularity and an event horizon, right? A strict point of no return. But a gravastar is a theoretical, exotic kind of star. It's almost the exact same size, and it exerts the exact same gravitational pull from the outside. But here's the kicker. It has no event horizon. Instead, the theory goes that it's filled entirely with dark vacuum energy. And because they lack that event horizon, they could potentially emit information. They might even have totally different signatures in their gravitational wave emissions, which means, with the right tools, we might one day actually be able to distinguish them from regular black holes.
So, I want to leave you with this really provocative thought. Are the monsters we're detecting in the dark, these ancient invisible giants, actually gravastars? Could they be the very source of the dark energy that is currently expanding our universe? It's wild to think about, but as our multi-messenger tools keep getting better, as we get better at listening to the ripples of gravity and looking deeper into the dawn of time, we might just find that the universe's absolute biggest mystery has been hiding in plain sight this whole time. Thanks for joining me for this explainer, and hey, keep looking up.